So now I'd like to cover a few of some basics of steel, just to make sure that everyone is kind of up to speed on some of the basic concepts. And so let's get started. You're probably all familiar with this now. The idea of what a wide flange, a W section is. We typically use those in architecture. They are, the flanges do not have a taper to them. Many times the web is thinner. The idea being that if we move the steel out to the furthest points of the beam, that's where we have the most bending and compression tests or stresses. And so we want to put the most amount of steel there. So in order to conserve the amount of steel that's used, we can reduce that center web thickness down until we're only dealing with some of the horizontal and other shear effects that might be induced upon that because of its shape and geometry. I think I've asked, but a lot of times people would refer to structural elements like this as I-beams. But in technical parlance, we talk about them as W sections or what would be more like the I-beam, that kind of S section. There's another shape that comes into play, and that is this kind of an idea of an H-beam. And an H-beam is really a W-beam with some other specific characteristics to it. But I want you to think about a W-beam or an H-beam as being a beam that can carry a vertical load. Its geometry, more close to the idea that the section properties in the X and Y direction, that it's kind of uniform. It's more like a column, so that it wants to bend in equal ways in both the X and the Y axis. And so we take a W flange, we stretch those top and bottom flanges out in order that it can perform better as a column. There's another whole world or way of looking at steel, and that's the idea of built-up sections. So we can combine all kinds of steel, U-shapes, C-shapes, L-shapes, in ways that can give us both the structural properties we want and also kind of the aesthetic appearance that we want. In this case, I'm illustrating one on the left here, which is actually caissons. These are that kind of inverted U on the bottom is actually, they have grooves on them, and they are piles that can be driven into the ground. I said caissons, but I really meant piles, to resist soil from infilling and excavation, many times to create a load-bearing surface for a building, all kinds of host of applications. And when they're really long, they may have issues with them having actually to support so much load that they need to be reinforced. So in this case, an I-beam has been welded to them, so that is a built-up section. But mostly for our interest, we're concerned with this idea of being able to build up these sections specifically to kind of the decorative and performance issues that we're looking for as architects on our projects. We also need to be aware of this idea of what happens at the connections. The joints of steel to steel are not arbitrary, and you should be able to recognize the difference between what is a shear connection and what is a moment connection. Engineers love shear connections. Moment connections become very complicated because what happens is we're transferring that twisting motion of the beam into the column, and that can make calculating when we have many conditions of moments being introduced into columns, that can make for the calculations of the strength of those assemblies very difficult. So we tend to favor this idea of shear connections, where we actually, if you look at the illustration number 1 here, that is a shear connection. The idea is we're only taking the downward load upon that beam and maybe some tension or compression load on that beam, but no moment loads. And in order to deal with those, we just bolted those connections together. We made specific efforts in the construction of the way we've cut this beam to make sure that we're not going to transfer any moment. So actually, if you look at this bottom, you can't see on the top flange, but if you look at the bottom flange, there's this cutaway section, and the flange comes up short of the actual column that has supported it. And that's so during deflection, none of the moment energy, that twisting moment energy, is delivered into the column assembly. But we can, in many cases, decide that we want that moment connection, that rigid frame. A good example of when we would want to be able to deliver that kind of moment energy into the column would be if we were creating what is called a moment frame, a way of resisting, acting kind of like a shear wall, but with an opening through it. So here we would have a U-shaped or two vertical columns, a floor beam, and maybe the next floor beam up above it, all welded very tight. And then they act together in order to create shear resistance or bending resistance in the vertical plane of the building. So they would be very important in bracing buildings for earthquake resistance and that sort of thing. You may also be well aware, especially when we compare this to things like heavy timber, steel is greatly weakened. Its weakness is actually the exposure to heat. Fires, which are actually a very common thing that we try to prevent in our architecture. But steel very susceptible to failure from extreme temperature. So here we have examples of beams buckling that have been exposed to fire. So we have, on the top, a catastrophic failure of the ceiling system. Looks like a kind of a warehouse fire. And if we look up close, we can actually see this idea of how the loads are moving through the assembly. So the beam becomes very weak. The beam is bending, and so that the bottom flange, while it gets very weak, it starts to buckle and deform. So we see that buckling on the bottom flange of the beam. Another one on this bottom left-hand side here, we see that the column is actually buckled from the heat. So it took, the load was still bearing, probably a multi-story building, but the load bearing on it actually exhibited by this kind of buckling. And it's probably happening up in this kind of top area here because that's where the most intense amount of heat is collecting, because it's hot air rises and the hottest air is up captured in that kind of a ceiling plane. So obviously we have to do things about that in order to make our building safe. So here we have one of the first basic treatments of our steel in order to make it fire resistant is this idea of a spray applied fire resistive material. The idea is that we're insulating the steel from the intensity of the fire. The material needs to be, obviously, that we spray on, needs to be non-flammable and have poor thermal conductivity in order to insulate. And it has downsides to it. It could be chipped or peeled away or deteriorate away. It is also aesthetically not very attractive. So it's probably one of the last choices we want to make when we're talking about architecturally exposed systems. But we do have other solutions to that idea when we want to see steel. And I don't have that image because it would look just like I'll show you in the future. But we can actually paint our beams with intumescent materials. And they can be in the form of paints, as I've said. They're coatings that you can put over the steel. And they lay very flat. But what happens is when they're exposed to heat, they begin to swell up. And they create a density in this increase of value and volume in order to insulate that kind of a steel connection. So intumescent paints are very typically applied to steel that we want to have exposed and yet have some degree of fire resistance to it. And another way, and probably for sure not the way we would want to do it if we were making exposed structural steel, would be to insulate or cover our steel beams. And one of the best materials to do, a common way, is to cover them with drywall. So we can actually add thermal insulation, non-flammable, things like rock wool, and then cover them with gypsum board or cement board. Gypsum board is a really good material to give us fire resistance, and we can continue to put layer after layer above it in order to increase the fire resistance of the assembly that we're trying to construct. And then the other way that we can deal with the idea of fire hazard and heat destroying the structural properties of our steel is the introduction of sprinkler systems. And this may come along as a requirement, regardless of the construction type, just as a code requirement for the inhabitant and use of the building system. So something to keep in mind. Next, we'll pick up on some kind of in-depth discussions about exposed structural steel as part of that continuing education reading that I'm going to have you do.